Welcome to today's Research Pays Off. I'll now hand it over to our speaker for today, Rita Lederle.
All right, thank you, Lauren. So my name is Rita Lederle. I'm an associate professor at University of St. Thomas, and we're going to talk today about the effect of putting low levels of recycled concrete aggregate, or RCA, in concrete pavements. So I got to switch it on the right screen there. Okay. Just to make sure we're all on the same page, I'm going to start out by just defining recycled concrete aggregate. So this is old concrete or previously hardened concrete. It might not be particularly aged, but previously hardened concrete that we are crushing up, and then we're using the coarse fraction of that as aggregate in new concrete. So the RCA, the recycled concrete aggregate, it will consist of the original aggregate from the parent concrete, or the concrete that got crushed, as well as the adhered mortar, which is what we call the old paste that's clinging to that concrete. We can use RCA to replace virgin aggregate or new aggregate in granular base. It's very common. And then also in new concrete as coarse aggregate. There are folks that look at using the fine fraction of crushed up concrete, but we are going to focus on only using the coarse fraction bay. It's much more common. It's generally accepted that using the fine fraction tends to result in problems. So why would we want to use RCA? There's a couple big arguments in favor. The first one is it's towards sustainability. So if I am using crushed up old concrete, I am not landfilling that concrete. And then I'm also not having to quarry or extract as much virgin or new aggregate to go into either my concrete or my granular base. So right there, reducing landfilling and then reducing the need for new materials, that falls squarely under sustainability. There's also a lot of places around the country that are facing aggregate shortages, or they anticipate having them in the future. So what this means is that metropolitan areas are running out of locally available, high quality, easily accessible aggregates. And when that happens, you either need to start importing aggregates from further away, or you need to start looking at aggregates that you had previously dismissed, or you need to find alternative aggregates that you have something else you could put in your concrete that you hadn't previously considered. So RCA can fall into one of those categories or multiple of those categories as something that maybe we weren't using in the past, but we need to start using now to avoid having some of the other options when we hit an aggregate shortage. And then finally, if you're using RCA, depending on your project, there's potential for cost savings associated with that as well. So some really good reasons why we might want to use RCA. There's also concerns about why we might not want to use RCA. And I'm talking about using RCA in new concrete. So RCA has very accepted use and very wide use as granular base, but we're focusing now on putting it in new concrete. So reasons why you might not want to do that. We know it changes concrete properties. And in the past, people put down some test sections of RCA, or they did some actual pavements with RCA, and they didn't always consider that it was going to change the concrete properties, and that resulted in some poor past experiences. Some folks had positive experiences, but a lot of folks, when they initially tried this, had poor past experiences. And so a lot of people said, we're not going to do this for a while. It's starting to see a resurgence. People are starting to look at this, but there's a lot of uncertainty. People want to know, is it going to have the performance that I need? Is it going to last? Will we have durability? What about consistency issues? If I make it 1 week and it works great, and then the next week it doesn't work because my RCA source changed. You know, last week I crunched up an old highway, and this week I'm crunching up an old building, and they're different. Is that going to be a problem? What if I had material distresses? What if the original parent concrete had ASR or decracking? Is that going to show up again? And sometimes we might know the answers or have educated guesses at the answers to this, but sometimes the people with that information and the people asking the question aren't necessarily talking to each other. So there's a bit of a technology transfer issue. There's an availability issue. We use a lot of RCA as granular base, and sometimes that uses it all up. You know, if I have an old concrete road and I grind it up, I am not going to get enough RCA to make both the base and the new concrete road from that old road. Now we have other sources of RCA, returned concrete that comes back in the back of the ready mix truck, demolition waste from old buildings. But we're also using RCA as granular base under asphalt pavements. So it's not always available. There is a lack of technical guidance on how to deal with how those concrete properties change. And then we have a specification issue. So there are specifications that just outright ban the use of RCA due to those past poor experiences. And there's other specifications that hold RCA to standards it cannot meet. Either the tests are inappropriate for use with RCA, or RCA just will never be able to do what the spec is wanting it to do. And so those are not an outright ban, but they're a de facto ban. And finally, if you look at all of these things, when you have uncertainty, when you have specs that make it difficult, the contractor is going to be reluctant. They don't want to necessarily take on that risk. So in the past, a lot of these things in the why not to use RCA column, that has been enough to make people say it's not worth it. Yeah, there are positives of reasons we might want to do this, but we're not going to go there. Now, with a huge push for sustainability, and as those aggregate shortages loom ever closer, people are starting to say, you know what, maybe it's time to look at it again. And so a lot of people are looking at how do I use RCA, but they're looking at high levels of replacement. So the graph below, I had my student worker, I told him pull 100 papers of recent publications on RCA and just look at what percent of replacement level they're looking at. He pulled slightly more than 100. He's a very ambitious student. And so he just said, okay, what percents do they consider in replacement levels? And most of them are looking at 100%. A lot of them are looking at 50%. So people are looking at these really high levels. And when we use a high level of RCA, we know there are changes. It's definitely possible to make good concrete using that RCA, but you have to really be thoughtful about it and consider it. You can't just throw it in there. So just doing that, as a direct one-to-one swap, if you don't consider it, bad things can happen. And so there's a lot of hesitancy and uncertainty around using those high levels. And then, as we said, those high levels aren't always even available. If we're using it up as base, it's not necessarily going to be available to do 100% replacement. But what about low levels? That's an area, there's some precedent for this in the asphalt world. So I know we're on the rigid side of the world. We're loath to look to asphalt for inspiration. But if we can swallow that and just see, what are they doing? A lot of places, if you have a RAP, a recycled asphalt pavement, ground up old asphalt, and it meets spec, you can put in, depending on your agency, 10 or 15%, and that's okay. The amount that we let people do that in concrete currently in a lot of places is 0. And we don't have a lot of research to say, well, maybe 10 or 15% could be okay. And so that's really what this project is looking at. What could we put into concrete? This isn't going to solve sustainability. This isn't going to solve an aggregate shortage, but it's going to help. It's going to make a little bit of a dent. And once you start using a small amount, maybe you learn some stuff, maybe you get more comfortable with it, and then we can start progressing towards using larger amounts. So this is a stepping stone. So we're trying to find, is there some replacement level where the RCA has a negligible effect? If we imagine a concrete ready mix truck, 10 cubic yards of concrete, and I replace a single particle with RCA, we don't think anything's going to happen. If I put in 10 particles, 50 particles, 100 particles, nothing's going to happen. Well, what if I replace 1%? What about 3%? What about 5? What about 10? Where do you start to get queasy? At some point, it's going to have an effect, but we don't know where that point is. So that's what this project is looking for. That's the big main question we're asking. If we're going to do replacement, we're going to need a specification to say, yes, this RCA could be or could be not used. And this project is never intended to define what that spec is, but it does let us create a roadmap of how would we get to a spec? What parameters should we start considering in a future research project to define that specification? And then another big goal of this project was to make sure that it was representing realistic use of RCA. So are we making sure that the decisions we're making represent how a producer or a contractor would actually want to implement this? So with that in mind, our overarching question, what is a low level that we could consistently use, or is there one? So based on our literature review, we found that at 20%, enough people were saying, hey, there's a change, that we could say maybe that's not a negligible change level. So we looked at 5, 10, and 15%. There's really not a lot of research out there on those levels. So we can't tell you which one is the right choice. And then we looked at 4 different RCA sources and we tested a whole bunch of properties. So I'm going to talk about those. So first off, this is the mix we used. And so when we came up with our mix. We were working very much in contact with industry partners, with a local ready mix producer, because we want this to be practical and implementable. So we wanted to use a standard paving mix that's already used, but we wanted to make sure that it had an aggregate gradation for which there was RCA available of the same gradation, so we could just swap them. We figured that being able to exchange like gradations of a virgin aggregate and a RCA aggregate was really the only way that this could be practically done with some level of control, but still not be so cumbersome that we couldn't implement it. So we were looking for a ready mix producer that had a mix that used a certain gradation for which RCA was also available in that gradation. An added constraint we put on was we wanted to make sure that the results that we found were implementable in a lot of parts of the country. And so up here in Minnesota, we're pretty blessed to have really good quality aggregates and really strong natural aggregates. And so a lot of our concrete is made with granites and gravels. And there was a concern, well, what if we make some concrete, we throw in some RCA, and the rest of the aggregate that's in the concrete, the rest of the control aggregate is so strong that we don't notice the effects of RCA. And then we say, okay, oh, you can use a certain level, whatever we find. And then someone goes and tries it with a limestone aggregate and they throw in some RCA. And now all of a sudden the negative effects of the RCA can't hide behind that really strong aggregate. So we wanted to use a limestone that's representative of aggregates that are available in a lot of the country, that's not going to be so strong as to mask the effects of the RCA. So we found a ready mix producer that had a mix that had a coarse aggregate that was limestone. The number 67 represented a gradation for which a lot of RCA was likely going to be available. The producer has used this mix before in the past on paving projects for MnDOT, so it's definitely representative of reality. The only difference was that this mix was developed for type 1 cement, and this project really coincided with the rollout of type 1L cement. So we actually acquired all of the materials, all of the aggregates, and then we said, wow, type 1L is hitting the market next month. Let's wait a month and let's get the type 1L so that these results are valid going forward. So the producer had not produced this mix with type 1L before. Once we got the cement, we did have to adjust our admixtures to account for that. And then two other notes. So the coarse aggregate was actually a blend of number 67 and number 4. With that number 4 aggregate, we removed everything retained on the 1 1/4 sieve. And that just allowed us to go down to 4x8 cylinders instead of 6x12s so that we could drastically reduce the amount of RCA that we needed to source and the amount of concrete we needed to make for this project. And then we used the sand from the ready mix producer, but it was delivered in 2 deliveries. They had very slightly different gradations. We don't think that had much of an effect, and I'll show you that, but just to note that. So this is the coarse aggregate gradation with that material retained on the 1 1/4 removed. So you can see the blend is what we ended up using. And then this is the fine aggregate gradation, and you can see that very slight difference between the 2 sand deliveries. Everything fit within the tarantula curve, again, wanting to be representative of what's used in industry. And so then we went to go source our RCA. And so the ready mix producer that we got the control mix and the control aggregates from, they had initially been producing RCA at 3 different plant locations. So 3 different types of RCA. But then, you know, we started gathering our materials in the fall, and then over that winter, they actually decided to shut down 2 of their RCA production facilities. So we were left with 1. And so that's material A. And then they also said, oh, and by the way, the gradation has changed slightly. It doesn't quite meet a 67 anymore. So that was our first material. And then so we started calling other folks and saying, all right, we need RCA. What do you have that meets a 67? And so material B, this is from another local ready mix producer. They actually do make an RCA that they put in concrete where they're allowed to, and it did not come close to a number 67. They're doing something completely different. And so they said, well, we can't give you that, but we can give you something else that's not intended for concrete, but it does meet your gradation criteria, and it's available, and we can send it to you, and it's RCA. And we were having a really hard time sourcing RCA, so we said, great, we'll try it out. So I don't want anyone to look at it and think that there's a ready mix producer that's using aggregate B in their ready mix because we're going to see that aggregate B tended to be the odd duck and is the only one that really had major effects. But this is not the material they normally put in their concrete. This is a different material that they produce for a different purpose. Aggregate C, another local ready mix producer that had an RCA that was close to a 67. And so these A, B, and C, they're from local ready mix producers in Minnesota. I already told you we've got really good aggregate here. And so there was a concern, well, what if all of these aggregates, the parent concrete from which they were made, very likely had really strong aggregate in it? What if that turns out okay, but if I were to use RCA from a lower quality aggregate, that it wouldn't work? How would we know? So we started looking around to try and find an RCA that was made from a parent concrete whose provenance we knew that likely had a lower quality aggregate in it. So this is an NRRA project. The TAP consisted of a bunch of different DOTs, and Missouri DOT very graciously said, well, we've got some RCA. It's left over from a different project. It sort of meets a 67. It's close. And we know the source of it. It's from the St. Louis airport, the crushed airfield pavement, and we know that it's a limestone. And so we said, great, that would be perfect. So they very graciously sent that to us. And so that was aggregate D. We looked at 3 different replacement levels, 5, 10, and 15%. Based on the literature review, we felt like those were our best shot. And then we're only replacing the number 67 portion of the coarse aggregate. We're doing a volume-based replacement. But to replace 5% of the total coarse aggregate, we actually have to replace slightly more than 5% of the number 67. So we did take that into account. So here are our coarse aggregate gradations. I'll draw your attention to the fact A, C, and D. So nothing, first off, nothing met the 67. A lot of them were close. But A, C, and D were on the coarser side, and then B was on the finer side. My computer just happened to pick a very different color for B than the rest, but a little serendipitous because B tends to be our odd duck, as I mentioned earlier. So we also looked at the coarse aggregate properties. So we have specific gravity, absorption capacity. You'll note that the absorption capacities are much higher and the specific gravities are much lower for the RCAs versus the control aggregate. That's to be expected because the RCA has that adhered paste on top of it, that adhered more to the old paste. So that definitely increases your absorption capacity. And then the percent fines, producers said they don't want to wash this stuff, but they also felt like they could make RCA that had a low enough fines content that they didn't need to wash it and it would still be acceptable to a DOT. So the TAP felt like somewhere in the neighborhood of 1 to 2% would be a reasonable limit on the percent fines. All of the producers were meeting that except B, again, because this aggregate was intended for something else. And so that one had a much higher percent fines, a much higher absorption capacity. And then when we ran statistical models on the results we got, we wanted some way to look at the effect gradation was having. And our statistical models would not allow us to put a gradation curve in the model. So we needed a way to summarize the gradation curve as a single number. And so fineness modulus obviously is not a perfect way to do that. But in this case, on the curves I showed you on the previous slide, A, C, and D were kind of clustered together and they were fairly close to the control, and B was much finer. These fineness moduli numbers show us A, C, and D clustered together close to the control, and B representing much finer. So we felt like fineness modulus in this case in particular was a good proxy for gradation. So we're going to use that to represent our gradation when we do our statistics. And then finally, Missouri DOT requested that we include Micro Duval because they do have a lot of experience with aggregates that are of lower quality or lower strength. They said that they have found limiting Micro Duval to something like 22% is a good way to ensure that their aggregates don't have a lot of issues. None of the aggregates, and so they actually were very willing to run this test for us. So we're really grateful that they did that. We sent it down to them. So they ran Micro Duval, and none of our aggregates were less than 22%, or sorry, greater than 22%. So they all met this criteria that Missouri has found to be useful. But we still wanted to see, is there any trends associated with Micro Duval? And so I'll talk about that later on as well. So the big question, can we use RCA? We're going to run all of these tests using the mix that we've developed. And before I show you the results, I want to talk to you a little bit about the statistical analysis we did, because I don't want you to read into the results trends that aren't actually there. So what I mean by that is if I were to mix a whole batch of concrete and make a set of cylinders and I were to break them, they would each be different. We expect that. We know that the concrete is going to have this inherent natural variability. So if all of our cylinders broke exactly the same, that would be pretty suspicious, pretty unusual. We expect them to have slightly different values. If I make a batch of concrete and I make two sets of cylinders, I break set one, I average the results, I break set two, I average the results. We know that all that concrete has the same strength. It's one single batch of concrete, but those two averages might be similar. They might be close to each other, but slightly different. And we know that that's the natural variability in the concrete. But now what happens if I make one batch of concrete, one set of cylinders, average the results, regular concrete, and another set with RCA, and I compare those two averages and they're close, but they're slightly different? Is that because of the natural inherent variability of the concrete, or is that because I used RCA? So statistics can help us make a confident assessment of the answer to that. You know, nothing's ever certain, but we were looking at a 95% confidence interval to be able to say, yes, no, the effects we're seeing are due to the RCA versus the effects we're seeing are simply due to the inherent variability in concrete. So to look at that, we used a method called analysis of variance, or ANOVA. This method compares all the results and says, are these within the range that we would expect of variability, or are they actually different? But it kind of tells us one of these things is not like the other, and it doesn't necessarily tell us which one is different. So we applied a second method to those results called Tukey's on a significant difference, and that lets us tease out, if we say there is a difference in these results, is it because A5 is different from C10, or is it because one of them is different from the control? And we decided we only care if they're different from the control. If they're different from each other, you know, one is higher than the control, one is lower than the control, and neither of them is different from the control, but they're different from each other, we don't care about that. We're only caring how they compare to the control. So I'm only going to share with you results that are statistically significantly different, where we can say with 95% certainty the RCA is having an impact. Another question that we can ask and answer with statistics is, are there any significant trends that relate aggregate properties to the results? So if I were to plot up a change in concrete property versus the aggregate property, and again, those aggregate properties I've repeated there for you, do we see a trend? And is that trend actually there, or is it just like we squint and it kind of looks like it's there? So with 95% certainty, there actually is a trend. This is called linear regression analysis. We looked at the correlation coefficient and the coefficient of determination. There is a technique called multiple linear regression where you can look at, well, what, if there is a trend, how much of that trend is due to absorption capacity versus specific gravity or micro Duval. Those models are not applicable in this case. They end up really unstable, and that's because our aggregate properties are not independent. So for example, if I have a high adhered mortar content, I'm going to have a higher absorption capacity and a lower specific gravity and probably a higher percent fines. So these are all interrelated, and so the models then can't distinguish between them very well. So we're just going to look at basic linear regression. And then finally, a note, so we're going to talk through the properties here. The statistical analysis, the ANOVA, requires that you have multiple replicates. So it's only usable on the hardened properties. We can't do it on the fresh properties, things like slump, because you only run one slump test, or we only ran one. So first up, I'll talk about air content. And then when we talk about freeze thaw, we can look at how the air content related to the freeze thaw results. So we ran both standard air and super air meter. You can see that typically the air content increased, but it was generally still within spec. And then the super air meter, we're looking for a number less than 0.2. Typically indicates good freeze thaw durability. And a lot of our super air meters, the test results were fine, except if you take an extra step and you go through and you say, well, is that result likely valid, or is there a possibility that it's incorrect? So there's a spreadsheet you can use to put in all your intermediate pressures. And we got a lot of results where the SAM device gave us a number with no indication there was a problem. There was one error, but all the rest of them, it spit out a number. But then if we go back and say, well, was that number likely correct? A lot of them flagged as no. So take the SAM results with a grain of salt. But in general, we were seeing that this concrete looked acceptable from a fresh perspective. And then I'll show you the hardened freeze-thaw results and the correlations later. We also looked at the slump test and the box test. So this went too far. Okay, so the slump test, we were seeing our slumps increase in almost every case. And that's really unexpected on a first glance. We know that RCA has a higher absorption capacity. So we would expect the RCA to suck up more water. And typically when you're using RCA, you expect slump loss. In this case, we were gaining slump. So we stopped, think about it. What's happening is we mix our concrete and then we immediately discharge and do our fresh tests. So the water is mixed in with the dry ingredients. You know, you run your mixer 3 minutes, you wait 3 minutes, you run it 2 more minutes, discharge, and immediately one student starts running slump, another one starts running box. And so there's no transit time, basically. You know, at the plant, we would add the water to the truck would drive out to the site, and by the time it's discharging there and you run slump, the RCA has likely had enough time to start absorbing that water. Maybe not get all of it, but start. There's no agreement in the RCA community on how long it takes for the RCA to absorb that water. And there's a big range of estimates depending on who you look at, but everyone pretty much agrees it's more than 10 minutes. We're mixing and immediately running slump, so these results are after about 10 minutes. That's why we think we're seeing our slump increase. We think if maybe we had changed the order of testing and slump had been run towards the end, we might have seen more of that slump loss. You can also take Ken Hover's approach that slump is completely useless and then just disregard these results entirely. We also ran box tests to see how this mix would consolidate. So interestingly, our control mix actually had the worst box test score. And then the most of the mixes that contained RCA did better. And so anything less than 2 is generally considered good. And then part of the box test is evaluating edge slumping. We just evaluated it on a binary yes, no, there is edge slumping more than a 1/4 inch threshold. And most of our mixes did have edge slumping. What we think was happening here, like I told you about with the slump test, we were running the box test immediately after discharging from the mixer. There was no simulated transit time. And so our mix was kind of loose. We think that that's the reason so much of this edge slumped, and that if we had waited and run the box test later and the mix had tightened up a bit, we might not have had that. We looked at relationships between all of the tests. So typically slump and box are not correlated because they're different mechanisms. They're measuring different things. Here we did find a correlation between them. But we also found that both the slump and the box test were significantly and strongly correlated with the air content. So we think the correlation we're seeing with the box test and slump is actually just the reflection that both of them are correlated with air. And then none of these had a significant correlation with any of the aggregate properties we looked at. When we move on to hardened properties, so compressive strength, that's the first one everybody runs and everybody looks at. And you can see our control group up here towards the top. Mix A5 really matched pretty well with the control, and everything else was lower. We did see a reduction in strength. That reduction was statistically significant in most cases. So we were seeing a maximum reduction of 38%. If you take it out to 56 days, that went down to 30%. Most of the mixes were lower compressive strength in the range of 15 to 25%. I will note that most of them still met 4,000 PSI at 28 days, so the AASHTO performance spec. A couple of them didn't. Everything met it by 56 days. We also looked at the rate of strength gain. How fast are these mixes gaining strength? The slope, not really slope because it's nonlinear, but the slope of that curve, if you will. We took the derivative of it. And most of our mixes had a reduction in strength gain. Another test that we ran on our cylinders during the compression testing was digital image correlation, or DIC. So before we put the cylinder in the compression tester, we spray painted it white, and then we just spritzed it with the black spray paint. So we get a really high contrast speckle pattern on the cylinder. And then we run the test as normal, but we film the test with 2 offset high-speed cameras. And those cameras are attached to a computer with some software that can track the movement of the speckle pattern during loading. And then it can do a bunch of fancy math, and it can compute and visualize the strain fields. So this image on the left here, this is a couple images before failure, and you can see that the strain, this is looking at strain in the horizontal or X direction. So the tensile strain pulling things apart where the crack is going to form. You can see that crack starting to form. And then I love this image because this is right literally at failure. You can actually see the hunk of concrete whooshing away. And there's the crack that initiated failure. And then this is the image right after failure where the cylinder has most definitely broken. So we can make some cool videos here. You can see this is that same cylinder. That crack is starting to form and then it fails. So I'll play it one more time now that you know what you're watching for is that crack formation. Play. Is it playing? There we go. So that crack forms, the piece whooshes away. So we took and we isolated the image right before failure. So it's really obvious when it has failed because it's in pieces. And so we went 1 frame before that. So that was the image before failure. And then we went 50 frames before failure. So where we had really nice steady state strain distributions. And we did a histogram. So we collected all of the strains on the strain field. And then we did a histogram and we looked at basically, we superimposed them and looked at the overlap. So anything, the blue histogram is the histogram of strains 50 before failure. The orange histogram is 1 before failure. The software does not let me pick the colors, unfortunately. And then the brown is the overlap between them. So if there's a lot of brown, these histograms are basically on top of each other. So this is the control group. And we can see when we look at the mixes containing the RCA, so this is RCA-A, there's a less overlap. And the orange histogram has shifted to the right of the blue histogram. So that's showing us that we have higher strains in general when we use RCA. And we see that trend plays out with aggregate B, aggregate C, and aggregate D. So these histograms are basically shifting, which tells us that the RCA samples have higher strains before failure. There is some actual behavioral change happening in those cylinders. What we think is happening is that there's more paste. So the volume of new paste to the volume of aggregate is the same, but the aggregate, the RCA, actually has a paste phase as part of it, right? It's the original aggregate plus that adhered mortar. And so we have more paste overall. We have less stiffness. So RCA tends to be less stiff, both due to that adhered mortar phase and the potential for microcracking in the original aggregate during the crushing process. So we have less stiffness, and we think that's giving us more strain. So overall, our compressive strength results, there is a statistically significant reduction in compressive strength when RCA is used, even at these low levels. That might be surprising because you might think, well, 5%, does that make that big of a difference? There's very few studies in the literature to compare with, but the ones that we did see, there was reductions on the order of 12 to 22%. We were seeing 15 to 25%. So we're right in there with what others have seen, that these low levels do cause a change in compressive strength. This is likely due to a combination of factors. So the aggregate itself is lower strength. The bond quality, or the ITZ, interfacial transition zone, can be affected. You have higher porosity, and then you have less actual rock in your mix because the RCA is that 2-phase material. So it consists of some paste and some rock. So less actual rocks. There is a lower rate of strength gain. And so some folks have suggested, well, the RCA, it has that higher porosity, maybe you'll get some internal curing, or the crushing process might expose some new faces and you might rehydrate some unhydrated cement in the adhered mortar. That might happen in some cases, but if it did, we would expect to see a higher rate of strength gain, and we didn't see that. So we don't think we're gaining any of those benefits. The other thing is it's not going to catch up. Right? So some folks have suggested, well, if you just wait 56 days or 90 days, the RCA will catch up. It will be as strong as the control. To do that, it would have to have a higher rate of strength gain, and it doesn't. So it is a lower strength, and it's not going to get there. Before we think, though, that's all doom and gloom, we're never going to be able to use this, let's stop, think for a second. What do we use compressive strength for? We use it not as a direct input in design, but we use it as a proxy. We use it to estimate flexural strength and elastic modulus. So let's look at those and see if those actually change when we use RCA. So here's flexural strength. This is a really different picture than what we saw with compressive strength. Our flexural strength, the control group, is right in here, the middle or the bottom of the pack. I will draw your attention, the control goes up and then it drops down at 28 days and goes back up at 56. If you were to connect all the dots without 28 days, we would expect 28 days to be a little higher. We think we got a low break at 28 days, and that's important because one single data point, this point right here, flagged as being statistically significantly different from the control. It was stronger, so that's positive, but if our control had not had that low break, we don't think anything would have flagged as significant. So our 28-day strength was lower than the 21-day strength. It did not follow the expected trend. If you look at the early age strength, so 3 days and 7 days, there was no statistically significant difference between any of the mixes and the control. The same thing for long term at 56 days. So it would be very surprising if there was no difference at all. And then at 28 days, magically there was a difference. And then we went back to having no difference. So we think we had a low break at 28 days. All of our mixes except one were greater than 600 PSI at 28 days. So that's that AASHTO spec, performance spec. So that's good news. And then we also looked at the standard correlation. So if I'm plugging in my compressive strength to try and predict my flexural strength, is this equation still valid? We were finding it was under predicting by about 4%. So that's pretty good. You know, this is a general correlation anyway. It's not 100% accurate. So this is a pretty reasonable, we think. So no real effects on flexural strength. We look at elastic modulus. The only mix for which we saw a statistically significant difference in elastic modulus were B10 and B15. And then we also looked at the standard equation for prediction. So a lot of folks and a lot of software programs use 57 square root of F prime C. We found that this actually over predicted your elastic modulus by 25%. So that's kind of a bigger deal. The 57 in that equation, that is a simplification based on an assumed normal weight of concrete, unit weight of 145 pounds per cubic foot. The unit weight of RCA concrete is typically less. And so a good question is, well, what if you incorporated unit weight? Would that yield you a better prediction? Potentially, we did not test that. But there's a great question of, is there a practicality of needing unit weight for your mix when you don't necessarily know what your unit weight's going to be during the design process because you haven't even necessarily identified a contractor yet, and they certainly don't know what they're going to have been crushing recently to get you an RCA unit weight. Other hardened properties we looked at, Poisson's ratio, nothing was statistically significant. Shrinkage, nothing was statistically significant. And all of our values there were within normal ranges. Coefficient of thermal expansion, we did see there was a statistically significant difference for aggregate B only. We also looked at durability properties. And here we looked first at freeze thaw. None of our mixes were statistically significantly different from the control, and everything passed. Everything was above 70 on the durability factor. When we look at were SAM and were air content good predictors of the freeze thaw durability? So if we're in this box here, air content test said we would be okay, and we were. This point, air content said it would not be okay, but it was still okay. Similarly, this box here, Sam said it would be okay, and it was. And then these points, Sam said it would not be okay, but it still was. So we cannot definitively say that the SAM and the air content are good predictors of freeze thaw because we don't have any data points down here where the tests said freeze thaw would not be okay and it wasn't. And you would want to see some points like that before you said that definitively you can use it as a predictor. But we are seeing good agreement, and it's we can say that if these tests say you'll be okay, we think you will be okay. We also looked at surface resistivity. So we have our control mix is up here and everything else is lower. And that difference was statistically significant. However, typically you take those numbers and you convert them to a risk of chloride ingress. And all of our samples, except one, were moderate risk. So it's kind of a distinction without a difference. Everything was moderate risk except one that was high risk. There is a question, there's some research that indicates if you're using RCA and fly ash in your mix, the correlation between surface resistivity and chloride ingress might break down in some cases. So there's a question about that. And then finally, just in case you're concerned about moderate risk, everything moved to low risk by 56 days, or most of them did, I guess. We looked at the rate of resistivity gain, and we were not seeing any patterns with replacement level, and there was no correlation with the aggregate properties. So taking these results, how can this give us a roadmap towards a specification? That's where that linear regression analysis comes in. So most of the correlations we saw, they matched expected behaviors. We didn't see anything really weird. We know what happens if you have a higher specific gravity, for example, how is that going to influence things, or a higher fines content. And those behaviors really matched what we would expect. Aggregate properties that related to mortar content, so things like specific gravity, percent fines, absorption capacity, those had larger coefficients of determination than the gradation property. And so we think that those are probably going to be more important. We had no significant correlations with our fresh properties, so I'm just going to look at hardened. And then just a final note, we could not use any of our data to determine if a property is a predictor. You would need a very differently designed study. So this was never intended to do that, but that would be some very interesting future work. So getting to a specification, how would we define a reasonable RCA? So how you want to read this table is if you take a property like compressive strength and you look at each of the aggregate properties, the green is the one that had the highest coefficient of determination. So that means that specific gravity is the property that most explains the variation that we saw in compressive strength. The red is the lowest one, so percent fines was the property that least explained the variation in compressive strength. And then occasionally there was no significant correlation, and so then we can't consider that property. So if one of our aggregate properties or several of our aggregate properties have a lot of green and yellow, those are probably properties we should be looking at. If they have a lot of red, that's probably not a property that's super important for us to consider. Fineness modulus, our proxy for gradation, was one that has a lot of red or a lot of no significant. That's actually really good news because that tells us that the idea of replacing the virgin aggregate with RCA of the same aggregate gradation band is okay, which is great because that's really the only practical option that we had. Specific gravity and absorption capacity both flagged, and the literature is pretty consistent that those do need to be limited. They're both proxies for mortar content. They're both incredibly related to mortar content, so you only have to limit one and then you'll necessarily be limiting the other. The literature suggests that a 5% maximum for absorption capacity is a good guideline. Here we found that 6% was working. But that somewhere in that neighborhood, that would be a good place to start for a specification, and your specification should probably include something about absorption capacity. And again, that will automatically capture specific gravity while you're there. Percent fines in a couple of cases really mattered, and others it didn't. And so 1% is probably a good starting point. Producers don't want to wash RCA, but they were able to demonstrate that they could achieve that fines limit of 1% without washing. And so we think that would probably be a good place to start for a specification. And then micro Duval did show up as being an important characteristic. We didn't have anything that had a concerning level of micro Duval. And so we aren't able to show with this study that what values you should consider. We would probably suggest you start with the Missouri DOT's recommendation of 22%, but you would hopefully in a future study, you would include aggregates that exceed that so you could see the effect. Obviously, we would want a specification to have eliminated aggregate B in this case, and micro Duval would not have done that, but the fines limit and the absorption capacity limit would have. So micro Duval would be eliminating other things that didn't show up in this study, but that it makes sense to consider. You could also consider other properties in a specification that we didn't investigate. But as you're starting to look at making a study to get to a specification, you shouldn't necessarily rule out properties that we don't have here. And then a specification is also going to have to address an idea of uniformity. When is one RCA different from another in terms of the effect on aggregate properties? When does it change that it matters? And then from a volume-based replacement, when specifically does a specific gravity change? Is that going to impact things? So a specification would need to think about that. So our conclusions and recommendations, RCA had no significant impact on replacement levels of up to 15% on the flexural strength, Poisson's ratio, shrinkage, and freeze thaw. It did have an impact on compressive strength and resistivity, but most of our resistivity was still that same risk category. And then we saw an impact on elastic modulus and coefficient of thermal expansion, but only for aggregate B. So we have to ask ourselves, was aggregate B something we would consider like a reasonable aggregate? Is that something we would feel comfortable putting in our concrete? Probably not, based on the specification limits that we're suggesting that you start with. Again, we're not suggesting a specification, but kind of a roadmap to it. Aggregate B should have gotten eliminated by a spec. And so if we look at reasonable RCA, we think 3 of the 4 were something you would probably be okay with putting in your concrete. At levels up to 15%, the only properties we tested that had an impact, or where the RCA had an impact, were compressive strength and resistivity. But again, and now resistivity was all in the same risk category. So also not really having an impact. So just compressive strength is the only thing being affected. That compressive strength gain was lower. It was not going to catch up. And the strength gain was due, or the strength loss, sorry, that was due to the RCA itself. And then resistivity, it did take a little bit of time to get to the low risk. There's the question of if the correlation is valid. Maybe you would need to consider, if you're using RCA, do you need a time limit? You can't apply de-icing salts until a certain age before or after paving. If you're paving in July, that's probably not a concern. If you're paving in October in Minnesota, you might need to worry about that. And then our SAM test and the air content test, they showed good agreement with freeze thaw durability. It seems like they could be used for RCA at these levels, although you should maybe consider repeating the SAM because we did have some invalid results. We found interplay between the slump, the box test, and the air content. And we noticed changes in these tests, even at these low levels of RCA. So even if the RCA is not causing problems with the hardened properties, there's a question of, will uniformity within RCA, within a stockpile, will that cause any construction or acceptance issues that would create a problem in the fresh state? Our recommendations is we think you can likely use reasonable RCAs at replacement levels up to 15%. We need to define what reasonable is. We need a specification to do that. This project can give a roadmap, but future research needs to define that. And then use caution if you have RCA, if you're using your compressive strength to estimate your flexural strength or your elastic modulus. Elastic modulus, we found under predicting by 4%, that's probably okay. But over predicting your elastic modulus by 25%, that's going to be a problem. So flexural strength, probably okay. E, maybe not so much. This project would not have been possible without a lot of help from a lot of people. So National Road Research Alliance funded it. Aggregate Ready Mix Association of Minnesota provided assistance and materials. We had a wonderful TAP that really made very big contributions to this project, definitely shaped it into a good, useful project. Bernard led the TAP, but all of the TAP members made valuable contributions. Brett Troutman, especially, I have to shout out to him for sending us RCA and for conducting the micro-Duval testing for us. We had a lot of good suppliers. Industry was very supportive of this research. And then a lot of folks at St. Thomas also helped make this project possible. So a big thank you to everybody. We do need to work together to do things. And I think this project showed that. So with that, I would love to entertain any questions. As you're formulating them, this is a picture of our old lab. We have a brand new, beautiful lab that's much larger than this, and you're welcome to come see it anytime. But I will always have some nostalgia from this picture for our old lab. So thank you.
Thank you, Rita. I do have a few questions now that have popped up into the chat. First few are from Jeff. Where were all the mixes batched in the lab?
They were in that mixer right there.
Okay. Did you plot the coarseness workability of the mixes?
In what sense? I guess I would ask.
That's
Probably
a good
no is the
question.
answer, given my question.
Okay.
Looking at a Power 45 or Shieldstone stacking, did you look at that in your mix, or were you just assuming it was close to a D67 mix, and so therefore it'd be the same?
Yeah, we did the tarantula curve
Okay.
for the control mix, but then nope, we did not do any of the additional plotting with the RCA replacement. We just did a swapping out like gradation with like.
Okay, thank you.
And then he also asked, did you look at the chlorides in the RCA?
We did not consider the chloride content of the RCA. That would definitely be, you know, as you're going towards a specification, I think that would be something that should be considered.
And then we've got a couple of comments here about an excellent presentation.
Thank you.
And then Daba asked, did you consider AC in the mix design to make water correction?
The absorption capacity, yes, we did. We measured absorption capacity and moisture content of everything, and moisture content the day before, and sealed up all of our aggregates overnight. And then we made moisture corrections. And so we think, as I talked about with slump, that's where we saw some of the issues with our slump test because of that.
Okay. I'm seeing a few more comments that this was a great presentation. I do see a hand, which I believe is Bernard's. Bernard, would you like to ask a question?
Yeah, can you hear me?
Yes.
Yes. Yep.
Okay. I just want to comment, Dr. Lederle, that you did not only address the purpose and the objectives of this research project, but you exceeded it. And we are highly impressed by the work you did.
Thank
I
you,
just wanted
Bernard.
to start by making that comment. Then secondly, some of the things that you may have been looking for in the low and moderate some of the properties enhancement of the ITZ, we found them to be obvious in the high replacements, the very high replacements. We found those enhancements, and we found a kind of zigzagged trend in strength gain, because with the aggregate avoidance, you had initial avoidance of the aggregate at very low strength. And over time, you will expect cracks to go through the aggregate. But at the same time, with the absorption and desorption, which happens that typically happens, that is characteristic of internal curing, you had the enhancement of the ITZ. So there was a zone which was supposed to be a weak zone that became a strong zone. And it kind of coated the aggregate and provided more strength, and we started to see aggregate avoidance again at high strength with very high replacement. So you wouldn't see that in low replacement, evidently. So what you did and what you saw was valid. So people would find those absorption and desorption with higher replacements.
Yeah, and you were seeing that at like 80%, I think, right?
Yeah, yes.
Yeah.
Correct.
And so if you look back at the very first graph that I showed you, of what people are looking at, not a lot of folks are looking at 80. And, with the zigzag that you saw, it's really interesting that there's this point where the internal curing mechanism kind of overcomes some of the negatives, and it's only strong enough in that certain zone, and people aren't looking in that area. It's the same problem with the low levels. People aren't looking there. When we're only looking at 50 and 100, we're not seeing those other effects.
Thank you again. We really appreciate your work.
Thank you, Bernard. And I really appreciate you and the TAP definitely helped on this project. So thank you very much.
Well, that was all the questions. Still a few more comments about the excellent presentation. If anyone else has anything that they'd like to chime in with, we still have just a couple minutes before the end of the hour. but I'm not seeing or hearing anything. So I think I will just remind you all to join us next month for the new non-contact testing device for concrete pavements presented by Quang Tran of Michigan Tech. That's May 16th, I believe. So thank you all for joining us. If you have stuck around, I know I see a few people have had to leave. And yes, we also hope to see everybody at the NRRA conference in just a couple of weeks. So thank you, everyone. Thank you, Rita. And have a great rest of your day.
Thank you.